Okay. Yeah. So yeah, thanks Andrew for the sharing of like all the basic information about TE. So here I'm introduce Phala Network. So it's actually a position as a extra security layer over TEs because yes, just as the security caveats has discussed. So actually, I think the philosophy here about TE is that first, there is no doubt that the TE is an add some extra security promise over the raw CPU. So uh, it's security features, so it's far better than the raw CPU itself. But actually, we do not trust T for no reasons. So because actually the fact is that there is some historical vulnerability reported for the TEs. So, but on the other hand, actually there is some I would say procedure you should follow. For example, there is some rules called responsible disclosure because, for example, when you try to find some vulnerabilities and you try to write a paper on it. So before you really publish that, you need to first like report that to the manufacturer. For example, we have to report that to the Intel first, and then we work with Intel to work on the patch, and only after that we ensure that all this patch has been sent out. We can publish the paper about it. So it's the responsible disclosure. So this means if we can like follow the standard procedure like to use these TEs, actually, I think the security level of TEs can be improved better. So, and in my talk, actually, I think I'm only here to answer one question. Here is that like, what's the difference between like using a TE from Phala Network or like from Secret Network, and like setting up a T hardware myself and like just to run it locally. So what's the benefits that our service can bring? So here I think yeah, the first okay, can you see the changes here? Oh, let me yeah. Yeah. So if you just like use a single native TE yourself, actually there can be some problem here. So I think the most of it is due to the internal limitation of TE itself. So first is that although TE provides the promise of like confidentiality, so the privacy of your data, and also like it provides the integrity of the program. Just as Andrew has just shown, you can see the hash of your program code and also the initial states of your program, so you can remotely verify that okay, all of them are not modified by any third parties. But the problem here is that the TE itself didn't provide the service availability promise. This means, for example, the TE hardware itself can be broken, and also like you cannot like prevent like these operators from like unplug your hardware. So this, if they do such kind of things happens, then like your service will down. And since your program is running inside TE, sometimes something worse can happen because like the TE itself provides some secret keys to seal your data, to store and encrypt your data to the disk. And such keys from TE is highly coupled with the hardware. So this means, for example, if you try to move the encrypted like disk image to another TE hardware, it cannot be directly decrypted by the TE. So if your previous TE hardware is down and is broken, then this means your data can be frozen forever. So yeah, so this is the cost of the all these security promise from TE. So this is the first problem. And the second problem is the vulnerabilities. So like all these vulnerabilities can mitigate all these confidentiality and integrity promise from TE. So this can cause some potential data leakage. So from if you are running something inside TE. So both of these, I think such problems cannot be simply ignored. So we have to uh, treat them with carefully. So this will be the problem if you try to run some TE yourself. So instead, I think the Phala here is that we wrap it as a service. So this means first we have a lot of TE nodes for you to use. So like if some of the nodes are down, we can very easily find some replacement for you. And on the other hand, we have some extra security like layer here to ensure that your program, for example, if one TE is down, your program can still be safely moved to another TE instance and resume to execute. I think this is very important for those projects who really serve their customers, because the customer don't want their data to be get frozen forever. So here, Phala now is one of the biggest TE network in the world. So now we have over 31K online workers, and this is still increasing. And also, like all of these workers, they need to be staked. So like these hardware operators, they need to stake Phala tokens to these workers. So these stakings are served as the security deposits, and also we have the tokenomics to encourage them to well behave, to provide high quality services. And now we have a live map of all the workers. So you can see that, so it's a P2P decentralized networks all around the world, and every node in it like come from our community, and all of these nodes, they are TE hardwares. So you can see it's from like Europe, China, Japan, also like North America here. So actually this is not a complete map because we cannot enforce our every nodes here to report their true IP address. But I think this already show that actually this is quite a decentralized network all over the world. Yeah. And yeah, so this is the extra security feature we majorly like provide here, is that so first, all these contracts in our platform is called AI agent contract. So every agent contract is run inside TE, and your contract is safe even if some of these TE workers are down. So if some TE workers are down, so the network will automatically move your agent contract to other TE worker that's still alive, so your service to the customers can still alive. Yeah, I will give a high-level introduction of how these things are happening. So first, like actually, if we want to use TE to run some program, so with privacy, so the very trivial solution here is that, so for example, we can generate some secret key directly inside TE. So it's generated and used only inside TE. So unless this key is fully compromised, so the outside world cannot see the secret key, so your program state is safe here. So, but this also means that like only this key is able to decrypt the states of your program and get it running. So this is how it works. So the TE generates the keys, and it's used one key for all the programs that's deployed to this hardware. And for every time it's tried to running these programs, so it's used its secret key to decrypt the states and do some calculation, update the states, and it's encrypt the states back and store it back to the disk. So this is how the whole process happened. Yeah, but there can be some problem here for this trivial solution. So the first problem is that, for example, if the T is down, then this can also means you lose the secret key forever. So then all these encrypted states can never be decrypted anymore. So since we cannot restore the original states of the program, so this means your program is also frozen, is also dead here. So this is the lesson one we can learn from this model, is that so do not totally delegate the key generation to one T, because if that T is down, then this means all these data encrypted by these keys will be frozen forever. Okay, so the second problem here is that since we use one secret keys to encrypt the data of all these programs, this means actually this bring a very high risk here. So for example, if this secret key is leaked, So for example, this TE hardware is like compromised, then this means the attackers can use these keys to decrypt the states of all these programs. So this increased the consequences that an attacker can create by like compromise a single node. So this is the second lesson we can learn here, is that do not use the same key for all the programs here, because like in the previous sgx.fail. The website, actually Andrew team do the work. So if like they compromise the keys, one key from one node, then this means all the secrets are leaked in this case. Yeah. But for our side, actually, we have some insight in this problem. Is that I think the most important things here is that we should decouple the program states from TE instance, so this program can be freely moved between different TE instances. So, and to achieve this, there is two concrete problems to solve. So the first is the key management. So how we generate this secret key and how we share it across different TE instances. And I think the second problem here, I will not discuss it in this case, because actually in smart contract scenario, so this is not a big problem, because all the smart contract states are naturally stored on the blockchain. So it's naturally shared across all the nodes. But the state storage problem, so when we encrypt these states, where should we store them, and how can we ensure that all these TE instances can get access to these encrypted data with correct access control? So this will be a problem for more general purpose real world programs. For example, like the AI model training and AI model inference problem. Yeah. So yeah, so let's focus on the key management problem in this case. So the solution from the Phala point, and actually this is, I think this is not this is not created by Phala. So this is first proposed in a paper called Hackathon, and this is adopted also by the Oasis network. Is that it's introduced a standalone key management service. So to do all the key generation and key distribution work. So instead of ask every TE worker to generate the key themselves. Yeah. So here, let's see like what's the things will happen like under this model. So first, like we can have a standalone key management services. So in Phala case, we also use TE to consist these services. So like we have some special node called gatekeepers. So they are the members of the key management service, and they are the root of trust of all the network. So like so we can see here, like here we can adopt a simple duplication model here, like the same key is shared across all the TE gatekeepers, and only if like the TE workers they are authorized, then like these keys will be shared to these workers for the real execution. So in this case, so even if like some TE workers are down, so like the KMS, since it knows all the keys, it can still find some replacement TE workers, and it's share the keys to them so they can keep the execution continue. And in this case, since like the keys are duplicated across all the TE gatekeepers, so only if there is at least one alive TE workers, TE gatekeepers, then like the whole network is safe. So it can still distribute these keys to the workers as needed. Okay, so about some TE, so what's the difference between the gatekeepers and the normal like TE workers? So the first is that like since we follow the on-chain governance, so all these gatekeepers, they need to be chosen by the on-chain council. So instead of like some centralized selection of these workers to be the gatekeepers. And second, I think this is partially covered in the previous talk, is that actually in every remote attestation report you get, there is one field so called like the quota status. So in the Intel case, there is different levels of this field. For example, in this example, this field, the value is called configuration needed. So this means you should like try to apply some patch of your firmware and like to change the configuration of your like BIOS or motherboard, or even like update the microcode for the CPUs to apply the patch for the vulnerabilities of your TE hardware. But in this case, like for the gatekeepers, actually we require all the gatekeepers to be the first level, tier 1. So the value is okay, and here the okay means this hardware is not affected by all these known vulnerabilities to the TE. So this means actually different TE hardwares also have different levels, and some we require those most secure TE workers to be the gatekeepers. So it has the lowest chance to leak these important keys. Okay, so then come to the second lesson is that we should not use the same key for every like applications in the network. So in our design, we generate unique keys for every contract running inside our network. So like the KMS itself, it's only take control of the root of keys, which called the master keys. And here we rely on some cryptographic function called key derivation functions. So these functions can be used to generate keys based on the master keys. But actually, all these generated keys cannot be used to infer any information about the master keys. So this is the one direction generation of the keys. And we use these primitives to generate contract keys for every different contract. And also you can see like actually you are free to deploy the contract to different TE workers. For example, in this case, contract 1 and 2 are deployed to the first cluster of TE workers, and contract 3 is deployed to another cluster of workers. And here the deployment means that the KMS will distribute these contract keys to the corresponding workers for real execution. Yeah, so this is a very high-level overview of like how we do key management in Phala Network. But actually, there is some more features to come since we are like heading towards more complex use case. So I think there will be 4 things to come. So first is the TE GPU support, because like in last December, NVIDIA has released the first commercial available TE GPU H100 series, and I think many teams are doing the experiment on that, because this extends the TE support from CPU to GPU, and this will enable a lot of new use case. And second feature here is called global key rotation, because you can see in last model here, all these keys, they are static. So this means these keys are there forever. So actually this is of very high risk, because you don't know when like the attackers can compromise like one of these nodes and extract the key. So one mitigation to that is to enable the key rotation. This means we can change all these keys regularly at certain interval. For example, we can rotate the key like of all the network like every 30 minutes. So this will increase the security level of the whole network, because this means the attackers, they need to extract these keys like within 30 minutes. And after they have done that, actually they can only use it for 30 minutes. But because after 30 minutes, all these keys will be changed. Yeah. So this will limit the attack interface of all the attackers. Yeah. So the third part is to how to enhance the KMS. So in our examples, we just used the most simple mode here, that the same key is shared across all these TE gatekeepers. But actually, the KMS itself didn't necessarily need to be like using TE. For example, it can be a purely like cryptographic KMS here. For example, you can just use all these MPC like algorithm. And since the KMS itself, the functionality of KMS itself is quite simple because it just need to manage these keys. So actually, like it can help mitigate many problems from the MPC. For example, MPC is kind of slow when you try to running some complex program here, but it's okay to use it to just like run the key management functionality here. So yeah, and the last case here is the complex program support beyond smart contract, because I said that like the smart contract, it didn't need to handle the state storage problem here because it's naturally solved in the blockchain use case. But in real world, the thing is different, so we need to handle this problem. Yeah. Yeah, this will be the general contents of my talk today. Thank you.
Hello, everybody. My name is Joshua, and I'm the Director of Tech Evangelism over here at Phala Network. So today I'm going to show you our initial template called the Red Pill AI Agent Contract Template. And here I'm just going to walk through the steps to getting started and how you can just deploy this really quickly and kind of go through the development process and the deployment process so that you know what's going on. So let's get started. All right, now. So as we're here is the Phala Network GitHub repo, and I'm going to look up the Red Pill template since the Red Pill template is the first template we're going to work with. So I go here, you can see this repo. I'm going to clone the repo here. So I'll copy this here, go into my terminal to Tintinland folder, and clone the AI agent Red Pill template. Now I'm going to open up my IDE. I'm using WebStorm for this, but I'll open up my project.